So what we're going to be doing today is beginning our look at finance. And our objectives in this part of the course are to figure out how to reduce complex financial transactions and to provide them with a common denominator. And what's going to make this a little bit complicated is that the payments can be made at different times, and we have to figure out how to discount payments that are made in the future, because as you may be aware, money in the future is usually not as good as money today. And secondly, how to deal with random elements in a payment stream. Usually the random element will be the amount that's going to be paid, but sometimes it can be the time at which payment is going to be made. And so you can't forget all your statistics knowledge, because those distributions are going to come back and determine the valuation of these various transactions. But what I want to show you today is how to begin to do this in Mathematica. We're going to do basically the same thing over the next 3 or 4 classes in Mathematica and R, and you'll see the advantages and disadvantages of using both of these systems of software. I'll also do a little bit on how to do this in a spreadsheet. All right, so the fundamental thing that Mathematica has going for it is something called a cash flow object. And what I'm going to do is, remember our friend Thread? Our friend Thread says take this and put it together, and take the second element here and the second element here and put it together, and put the third here and the third here, etc. So if I just thread this, I get the 0 hooks up with the 1 hooks up with the 1, the 2 hooks up with the 1, and the 3 hooks up with the 1. And what this is saying when I now wrap a cash flow around it is this is representing a payment stream in which you get $1 every year for 4 times, at time 0, at time 1, at time 2, and time 3. The first element in each of these little lists is the time at which the payment is made. The second element is the amount of the payment. Okay? So that's the first thing you have to remember what these arguments mean. The first element is the time. The second element is the amount. And you're just going to represent it as a nested list and wrap a cash flow around it. Okay? That's sort of the object in Mathematica with which we work. Once we have something represented as a cash flow, it's very easy to figure out what is the value of that cash flow today. All you do is, the key command you need to remember is TimeValue. Okay? TimeValue is sort of a generalization of what some people call present value, or what under other circumstances is future value. In Mathematica, this all gets unified under the idea of time value. And time value, in its simplest form, has 3 arguments. It has something to represent the cash flow, which is this CF, which we defined up here. It has an interest rate, and it has a time at which you're making the measurement. So the idea, what this is saying is, what is the value of this CF cash flow today, assuming that money grows at a rate of 5% per year. If you were to stick $1 in the bank today, you would find yourself with $1.05 a year from now. Okay? And so it magically does this computation for you. Okay? So it turns out that this stream of 4 payments isn't worth $4, because this payment in year 3 isn't worth as much, and the 2 and 1. And so it's saying that the value today is $3.72, meaning that you should, if you are a logical, rational person, be indifferent between getting $3.72 today and getting this cash flow with certainty over 4 years. Okay? With me on that? Everybody with me? Okay. You could also do this computation by hand, okay? Or by as hand as we get in here. And by doing it this way, look, you're saying take these numbers 0 to 3, make those the exponents of 1.05, and make that the denominator. So if I just do this little piece, you'll see that this creates a list of numbers. This is the value of the first payment at time 0. This is the value of the second payment at time 1. This is the value of the third payment at time 2. And this is the value of the fourth payment at time 3. And then we're just going to total all those up. And fortunately, these match. Okay, so conceptually that's what you're doing. And you'll often see, by the way, people write this. If you look at books on the subject that aren't using Mathematica notation, you'll see them write this as something like this, where they'll say, they'll let I or t be some index, and they'll say let t go from 0 to 3, and they'll basically have some cache thing, and maybe they'll put a subscript on that, and then they might have some discount factor, or they might write out the discount factor and say it's 1.05 to the t. So a lot of times, if you're looking in books, you're going to see them using what is called sigma notation, which is just a fancy way of saying add it all up. As you know, I'm not going to be using a lot of this notation. I might do so periodically. The other way, by the way, to think about this is, remember we've seen dot products in our lives, where if I say what is 3, 4, 5 dotted with 6, 7, 8, remember what this does? We multiply the 3 by the 6, and the 4 by the 7, and the 5 by the 8, and then we add up all the results so that I get 18 plus 28, which is 46, plus 5 times 8 is 40. So I think I get 86. Good. So you can also think of the cash value as the dot product of the payment vector, which is 1, 1, 1, 1 in this instance, with the discount vector, which is this thing. Okay, does that make sense? All right, so there are lots of different ways of denoting this idea, but the key point is that really what you're doing is you're just taking the cash flows and discounting them according to some time factor. All right, so that's a very basic problem where we took a constant payment. But what if the payment times aren't regular and the payment amounts aren't regular? Okay, so this is not hard. Here we're going to represent a situation in which the payments are made at time 0, time 4, time 5, time 6, and time 11, and the amount of the payments are -10, so we can represent situations in which maybe you're making a loan to somebody and you're giving them $10, and these are the paybacks. You're getting 2 and 6 and 4 and 3 at each of these times. So that creates our CF2, and we can now compute the present value, that is the value at time 0, of this cash flow, discounted now with an interest rate of 4%. Okay? And we get 1.75. We could also say, I wonder what this would be worth if we just let it sit for 100 years, and it would be worth $88. Okay? Or we could ask ourselves, what if we discount it not by 4%, but we assume I could earn 9%? And then actually our value is negative because this payment is starting to look different than it did before. And again, instead of doing the computation using time value, we could do it by hand, as I've done here, where this is sort of a compact notation. It's actually calculating the value of each of the payments, and then we just add them up, and we get the same number that we did before. Okay, so what I'm showing you is that yes,
the value of -10 should be higher. It should at.
It's being paid today.
I'm sorry. Yeah.
Okay, the -10 is being paid today, so no matter what discount rate you use, it's -$10. Right? And by the way, supposing you you wanted a formula. Supposing I want to say for any arbitrary interest rate R, what's the time value? And Mathematica will give you a formula. Okay, this is one thing that R doesn't handle, remember very well, is symbolic computations. It's really good at dealing with numbers. It's not good at creating the formulas by which those numbers were computed. So, and you can use the two of these things in a complementary way as a result. Okay? All right. Variable interest rates. Okay, sometimes the interest rate is not constant. It might be one number during one period, and you might have another spot interest rate during some other period. So how do you handle that? All right, so let's deal with a situation in which we have a cash flow where $4 is paid by time 1 and $5 is paid at time 2. If we now discount that by saying that for the first period, the interest rate is 10%, and for the second period, and I'm trying to remember why on earth I did it this way, what is the numeric value of 17/55? Is 30.9%.
So you broke usury laws. Okay.
Yes, but maybe I want a title lender or something. Not title lender, a car title.
Pawn shop.
Pawn shop.
They
All
can
right.
have
Or
240% interest.
yeah, they're real high. The value of this is $7.1. Okay. What else could I show you? I could show you accumulated value or future value. All right. So we've got something a little new here. Supposing that your payment is constant. I don't have to deal with variable payments. Well, I showed you one way you could do that. You could just write 1, 1, 1, 1, 1, 1, 1. Or, you know, if the payment was $20, I could write 20, 20, 20, 20, 20. Lots of things I could do. Or I could say, you know what, this is really what we call an annuity. The idea of most annuities is that they pay a certain amount of money for a certain period of time. So there's a way of representing an annuity in Mathematica, and it actually has its own little function name, which is going to be confusing, okay? There are two kinds of annuities in the world, and for historic reasons, they have horrible names. There is a regular annuity, sometimes called with the horrible name of an immediate annuity, and there's an annuity due. What's the difference between them? An annuity, or its exact equivalent, an immediate annuity. The payment is made at the end of the period. And you can see why this is why the term immediate is just horrifying, but that's life. Okay? So annuity or annuity immediate, payment made at the end of the period. Annuity due, payment made at the beginning of the period. Okay? There is no way that you just have to memorize that fact. Okay? So if you have, what this is saying is I want an annuity which pays $1 for 5 periods. And I want you to represent that as a cash flow. Basically, we're going to convert this compressed notation of that payment stream into a more explicit notation of that payment stream. So that's what we're doing here, and you can see what is this doing. This is saying at time 0, we're getting $1, time 1, we're getting $1, time 2, we're getting $1, time 3, time 4, we're getting $1, and it's going to tell you, hey, I'm closing it off. At time 5, you're getting nothing. Okay? So what I've done is to convert an annuity due object into a cash flow. A lot of times you do not need to do this. You can work directly with the annuity due. For example, I can say, what is the time value of an annuity due where I'm getting $1 for 7 periods, discounted at 10% right now. I don't have to convert it into a cash flow object. It's going to do that internally, and it's going to tell me that it's 5.35. But if you're like me and you sometimes can't remember, in the old days, now I remembered, what's the difference between an annuity due and an annuity? Or there are actually more complicated specifications of an annuity, where what if the payment is made 4 times a year? You can convert it into this cash flow form, which is easier to understand. It's more explicit and informative. Okay, so you can take, once you've either, if you state this as an annuity due, or you convert it into a cash flow, once you've done that, you can say, hey, what's the present value of it by setting the measurement time to 0. And here what I'm saying is, okay, what's the present value of an annuity due that pays 5 times? And it's going to tell me it's $4.16. With me? Okay. Here's one. This is a little more complicated. This says, what's the value of an annuity? It sort of pays $1 each year, but it breaks it up into 2 chunks, and it's paid 7 times. So if I look at the cash flow representation of it, it's going to tell me you're getting half a dollar at time 0 and half a dollar at time 1/2 and half a dollar at time 1, etc. And in all, there aren't 7 payments made. There are actually 14 payments made. Let's count them to be sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Thank goodness it came out correct. It closes it off. And so the number of payments made is this number divided by that number. So if you have something like that, it can actually compute the value of that. Let's see, what is this? Why did I do it this way? I'm measuring the value of this annuity at time 2.5 for reasons that I do not recall. All right. One more. This is like, I swear, this is like a semester's worth of a business class in just 15 minutes. But it's so easy this way. Internal rate of return. People often speak about what's the internal rate of return. What do we mean by the internal rate of return? We mean the interest rate, assuming there is one, which, if you made that the second argument of the time value function, this is not the classic definition, this is my definition. If you made that interest rate the second value of the time value function, the present value of the cash flow would be 0. That is, this is a net zero investment. And this is often, what this is saying is, it's as if you were, if it says the internal rate of return on a project is 7%, what you're really saying is you will break even on this, assuming you could earn 7% on your money. So, let's see, what on earth have I done here? I have created a function called project value. Let's actually read what I did. I'll be using a project in which payments of $100,000 and $50,000 are made at times 0 and 1, and which benefits of $20,000 a year are received for 6 years, and then a final benefit of $70,000 is expected at time 9. And what I want to do is I want to figure out what is the internal rate of return on this investment. So I'm going to set up my cash flow. And here I'm just, we've seen constant array before. Constant array is really an easy function. It just says make 6 of these. It's exactly like rep in R, except rep in R, the arguments are in the reverse order, just to confuse you. And we've seen join, I think, before. Join just says take 2 things and put them together. It's kind of like C in R. It's a way of combining things. So, there we go. And so what I'm doing here is I'm saying make a function that computes the value today of this cash flow using some arbitrary interest rate I. So if I say what is the project value if the interest rate is 10%, it's going to tell me it's negative 36,000. What if it's 1%? Then the value is 29,260. What if I were to plot the project value as a function of this interest rate, letting the interest rate go from 0 to 0.1?
You need to change the 0.01 to an I in the project value.
Absolutely right. All right, and so it looks like it's crossing at about 4.0, I just think it might be around 4.24028%. And find root, that's what find root's job is. It's to figure out where it crosses 0. Okay. In the book that I'm going to ask you to take a look at, that I'm having scanned now, this is the Promislow Actuarial Mathematics for Fun and Pleasure book. It's got an elaborate discussion about how technically there's another technical feature, because actually in some instances there are multiple interest rates that will solve this, and he has a way of figuring out which interest rate you should use in those circumstances. As a practical matter, this is extremely rare to come up, and it's just the actuary being picky, which is a good thing, but not something that need burden you. If you start at 0, you're going to get the right answer almost all the time. Okay. I think I should stop and give you an opportunity to ask questions about what we've done so far, or say, how do you do X, or something like that.
So just this last one, it's calculating that if, let me see if I can explain it. So if we had a 4% interest rate on the money, then we get our money back.
That's correct. That this cash flow, where you're paying out 100,000, you're paying out 50,000, but then you're getting this income stream. That's basically a break even at 4%. If you invest all of this money or have to borrow at 4% to get this money, at the end of the day, you'll come out about even.
But if you can, okay, yeah, but if you can invest that other money to a higher interest rate, you can get the idea.
Okay. So it's a useful construct, is this notion of an internal rate of return. Other questions? Okay, let's do a problem. I'll do a problem with you. I want you to tell me the value of a payment stream that pays $2 every year starting right now for 4 years with a discount rate of 8%, and I want to know the value today of that income stream. Want to volunteer an answer?
I didn't get the numbers, to tell you the truth.
Okay, $2, 4 payments starting today. 8%, what did I say interest rate was? 8%? I said 5%? I did not. I said 8%. 8%, all right. What's the first command I'm going to write if I'm writing from left to right?
Time value.
All right. All of these, they're time value problems. In Mathematica, the good thing is you don't have to remember if it's time value or present value or accumulated value. It's all time value. All right? So that's a good start. What is the second and third arguments to time value? What's the second argument?
Yeah.
What is it?
First,
That's actually the first
the
argument.
second's the interest rate. and
Second's the
third's
interest rate, which is 0.08, right?
is the
And
year
what's-
you want to predict, or whatever. Yeah, I mean that's what it is, but I don't know the word that you go.
Time at which you're
It's the measurement time. It's
Measurement
when
time.
it's like this is the common denominator. We're bringing everything back to time 0. Okay, that's how you should think of this.
Well, yeah, that's the most valuable.
All right, and what goes here in the first argument slot?
Cash flow.
We could do it as a cash flow. Okay, now what do I do?
Annuity.
Okay, you can do an annuity. Should I write annuity or annuity due?
Annuity due is what you used earlier.
I did, but maybe I'm tricking you now.
Why would you do that?
I wouldn't, but I could. It's an annuity due because the payment starts right now. Okay, and so
Yeah, I should know both.
is it this or is it this? I'm sorry, is it this or is it this?
2-4.
It's 2-4. It's a little bit confusing because in cash flow time goes first, and an annuity due it goes this way, right? And I think this is actually a design. I would not have designed the function this way, but so we can wrap a cash flow around it, and we can. By the way, this is exactly what you should do. You should just check that you got this right. Is this right? Yes, this is 4 payments. Okay.
Well, I guess the benefit of doing it that way
Yeah.
is that you also get to see that there's a 0, 2, so you can verify that you're you put the 2 first or the 4 first. Did the money go first or the?
I agree.
years?
I often wrap with cash flow, even though it's not necessary. So, if, for example, I can do this computation and I don't need the word cash flow in there.
Oh,
And if I do it this way, it'll come out exactly the same. It's just sometimes it's helpful to do this. That's all I'm saying. All right, well, that was too easy. Next one. I want you to tell me the value of a cash flow that pays the same, that pays 0 times 0, $1 a time 1, $2 a time 2, $3 a time 3, etc., up to 10. The last payment is made at time 10. So this is sometimes called an increasing annuity, where there's a linear relationship between time and payment. And actually, I'm going to change the problem a tiny bit. It's 100 times.
Could you just repeat the whole thing for a
Oh,
second?
so we can't just write it out, yeah. 'Cause
The-
it's the first thing that's right.
The value of an annuity or a payment.
I mean, I can still do it. It's just gonna take me.
Yeah, well, you might think there's a more efficient way.
99 bottles of beer in the one sink.
Value of payment stream of $1 at time 1, $2 at time 2, ... and $100 at time 100. Discounted at R at time 0. You want to put their answer on the table yet or not yet?
I just remembered why I sit over there to plug my laptop in.
I don't know the function.
Okay.
What would you do, like, to make X go from, oh, is it
Yeah,
table,
that's the
table,
issue I'm
or-
stuck at. Where do you go from next? He's right now. What's the answer? Oh, you.
What should I put? There's a little space here for me to put something else.
100.
Let's read up on that table command. Table. Let's look at some examples. I squared from 1, I goes to 10. Goes 1, 4, 9, 16, 35. Let's see here. Let's find another example. Here's not a bad example. 10i plus j is I goes to 5, j goes to I. What do I want? What form do I want my data in? Don't I want something that's going to go inside cash flow?
Yeah.
And what's the first argument of each of these little listlets in cash flow?
1.
Well, it's not 1. They're not all made at time 1. What time is the payment made in this?
Oh, sorry. Yeah.
Isn't it made at time t? And how much is paid at time t? According to t. So if I do that, I get what I want. There are lots of other ways of doing this, but that's one simple way of doing it.
So in R, I would have used the seq, the sequence command. I think, right? Is that the?
Yes, except it's a.
And then I would have done a dot between the
Yes.
100 dot.
Yes, and
100.
we can do this in Mathematica. Here's how I could do it this way. I could say thread, range 0 to 100, range 0 to 100, and then I could wrap this up in a list. And that would be, so this is sort of a more R way of doing it. You can do it in Mathematica too. So now that I've got that, okay, let's call this, I don't know, CF class. Now what do I do?
Then you just wrap a time value around it.
Yeah,
All right,
just
time
do-
value, CF class, now what?
What is the interest rate again?
R.
R, say then you put R, then comma 0.
And I remember to close my bracket. And that's not right. Because I didn't write cash flow. Let's wrap a cash flow around it. now if I evaluate this, I get an elaborate expression. But if you look at it, look what it's doing. It's saying it's $100, but we're going to discount it by 1 plus r to the 100th, plus $99, but we're going to discount it by 1 plus r to the 99th, etc. And now if I wanted to, I could plug in a particular value of r, say 7%, and it'll tell me that that payment stream is worth $216.47. Okay? So, that's what we're going to be doing, and you can see kind of where we're heading. We're going to do more on annuities. We're going to do probabilistic payments. We're going to look at a piece of code called actuarial value. We're going to be doing expectation. We're going to be doing simple life insurance problems, more complicated life insurance problems. We're going to try to automate. Where's the part on options? Must be in a different notebook that I haven't integrated yet.
Like stock options?
Yeah, like stock options, right?
You just wait until it rises really high and then you buy it.
Well, no, you buy it before it rises really high.
No, not at the option. The option gives you the option to buy it at a low price, so you want to buy it when it's highest. So if they give you an option to buy 800 shares of stock at $1, even though the market value is $10, you want to wait until the market value has gone all the way up. That's the option I'm thinking of.
Yes.
I don't
No,
know. There's probably other options.
Right
too.
there, that's what you've described as a call option, and there are put options. But that's fine. So someplace in here is, I guess it's this. Anyway, we'll get to option pricing so that you understand how to, all these derivatives that are out there that people buy and sell and that were allegedly the cause of financial crises, etc. We'll learn a little bit about how to think about pricing derivatives. And so the goal here is to make you feel comfortable with pricing somewhat complex financial instruments in Mathematica and in R, and so that and a little bit on spreadsheets, so that you feel like if someone hands you a transaction, you can understand what's going on. Okay. Alrighty, I will see you next week.